Today we have Proposition 13 of Book 2. Before we get started with the prop, I want to explain something that you already know, but just to remind you, for me it was a little difficult. That if this equals this, then if you put this over on the other side, this is less than this by this. So in this case, in this proposition, we're going to say that the one square is less than two other squares by this amount. Okay, so if a square is plus twice a rectangle equals two other squares, that square alone is less than those two other squares by twice that rectangle. Okay, basic thing. It was hard for me. And then we're going to use this proposition, proposition 7 of this book, that if there be a line and it be cut at random, the square on the whole line plus the square on one of the segments is going to be equal to twice the rectangle contained by those two, namely the whole and that segment, plus the square on the other segment. Let me just remind you of the chunks here. This chunk plus this chunk is going to equal to this gnomon plus this chunk and this chunk. Okay? Because this is overlapped twice. So this is the rectangle contained by this, and this is the rectangle contained by this and this. Just you can review the prop. And the other thing is this proposition was difficult for me. So I think what you're going to have to do is look at this video and also read the book pretty well. But it's pretty cool when you take your time with it. Okay? So here's the enunciation. In acute angle triangles, the square on the sides subtending the acute angle is less than the squares on the sides about the two angles taken together by twice the rectangle on one of the lines, namely that upon which the perpendicular falls, and the line between that perpendicular and the acute angle. Okay, so let me explain here by using one. We're going to have two cases. I'll explain in a second. So here you have a triangle, and here's the acute angle. So here's the side subtending the acute angle. Thus, it is required to show that the square on this line is less than the square on this line and this line by twice the rectangle contained by this line and this line, because we're going to drop a perpendicular here. Okay? So twice the rectangle contained by the line upon which the perpendicular falls, and the line between that perpendicular and the acute angle. Okay? So let me do it in both cases. Let me drop the perpendicular and then explain in both cases again. So we'll drop the perpendicular. Okay? And here, it's a different case. Here's the acute angle triangle, and this is the side subtending. What happens when you drop the acute angle? Okay? Get something like this. Okay? So I'll explain in both cases here real quick that in this acute angle triangle, the square on the side subtending the acute angle is less than the squares on the sides about the acute angle by twice the rectangle contained by one of the sides, namely that upon which the perpendicular falls, and the line between that cutting perpendicular and the acute angle. Same thing over here. Here you have our acute angle triangle. The square on the side subtending the acute angle, this blue line, will be less than the squares on the sides about the acute angle by twice the rectangle contained by, in this case I'm going to do a little reverse, the line between the cutting perpendicular and the acute angle and that side of the acute angle. Okay, twice the rectangle contained by this and this. Great? Now, before I get started with the prop proving this one here and that one, remember, this is going to be these are all right angles. So we're going to use proposition 47 all over the place. Okay? So here you have a right angle triangle. So the square on the hypotenuse is equal to the square on the sides. Here you have a right angle triangle. The square on the hypotenuse is equal to the squares on the sides. Here you have two right angle triangles. This one, so these two squares are going to equal to the square on the hypotenuse, and this one. So these two squares, the squares on these two lines, are going to equal to the square on the hypotenuse. Okay? So that's not a problem. So now let's set about to prove this proposition right here when the perpendicular falls within, okay, within that triangle. Okay? So look at this. We're going to use this proposition. We have a line, and it's cut at random. We know that the square on the whole line plus the square on one of the segments is equal to twice the rectangle contained by that whole line in that one segment, plus the square on the other segment, okay? Just like we said over here. So, the square on this plus the square on this is equal to twice the rectangle contained by this and this, plus the square on this. Let's add the square on this line to both sides of the equation. Equals added to equals are equal. Therefore, the square on this plus the square on this plus the square on this, look at that, is equal to the rectangle, twice the rectangle contained by this and this, plus the square on this and plus the square on this. Look at that. Therefore, since, like we said before, these are all right angle triangles, and the square on this equals the square on this, and the square on this, and the square on this equals the square on this, and the square on this, we know then that the square on this plus the square on this, because the square on this is equal to the square on this and the square on this, is equal to twice the rectangle contained by this and this, plus the square on this, because the square on this and the square on this is equal to the square on this. So you get that? So the square on this plus twice the rectangle contained by this and this is equal to the square on this and the square on this, which is to say, like I showed you earlier, that the square on this is less than the square on this and the square on this by twice the rectangle contained by this and this. Okay? Again, the square, it was just proven now that the square on this is less than the square on this and the square on this by twice the rectangle contained by this and this. Great. That's the first case. Now in the second case, when it falls outside, okay? So here you have an acute angle triangle. Here's the side subtending the acute angle. Thus it is required to show that the square on this is less than the square on this and the square on this by twice the rectangle contained by this and this. Let's set about proving that. Here you have a straight line cut at random. Therefore you know that the square on the whole plus the square on one of the segments is equal to twice the rectangle contained by that whole and that segment plus the square on the other segment. Great, those two things are equal. Let's add the square on this line to both sides. Therefore, the square on this, let's do it this way. The square on this plus the square on this plus the square on this is going to be equal to twice the rectangle contained by this and this plus the square on this and the square on this. But remember, as we said earlier in the proposition, this is a right angle triangle and this is a right angle triangle. So the square on this plus the square on this is equal to the square on this plus twice the rectangle contained by this and this, which is to say the square on this is less than the square on this and the square on this by twice the rectangle contained by this and this. Thus we have seen that if there be a acute angle triangle, the square on the side subtending the acute angle is less than the squares on the sides containing the acute angle, added together, by twice the rectangle contained by one of the lines, namely that upon which the perpendicular falls, and the line cut off by that perpendicular and the acute angle here and here. Okay? Look, I know it's a complicated plot. It took me a long time to prepare this video because I just didn't want to make any mistakes. I think I did it pretty well. Okay? So, quod erat demonstrandum. If there be acute angle triangle, the square on the side subtending the acute angle is less than the squares on the sides containing the acute angle by twice the rectangle on one of the sides, namely that upon which the perpendicular falls, that whole line of the original triangle, and the line cut off between the perpendicular and the acute angle. Quod erat demonstrandum. Thank you so much. Bye-bye.